So, hey everybody, welcome back to HPC Tech Shorts, the engineering water cooler here in AWS. This week, I'm joined by Rashika Kheria, who's a senior software dev manager in Annapurna Labs in San Jose on the west coast of the US. Rashika works in she works on a whole pile of amazing software that helps machine learning applications run performantly in the cloud. And of course that, because most of the machine learning model training is like at a massive scale, and it uses NVIDIA's communication collectives library, Nickel. That means that we get to talk about my favorite topic, which is EFA. So, hey, Rashika, thanks for joining us today.
Thank you, Boo, for inviting me. So yeah, I'm very excited to be here. I think you have covered everything in the intro, so I'll just dive into what we do here. So our team focuses on enabling and providing software for running distributed ML applications in the cloud in a performant way. So we enable them to use a fast interconnect called as elastic fabric adapter. And apart from that, we also develop software technologies to support our in-house accelerated devices called as Trainium, so that they can do fast machine learning training at a very large scale.
Machine learning has always fascinated me because it is intensely data-driven. So that means there is, when we're training these models, we're moving massive amounts of data around on a network. Can you give us some kind of
just to understand the scale of ML training? I think we have to understand the trend on what ML models are going towards. So the best way to put it is like the ML models are growing way faster than Moore's law. What that basically means is that every 2 years, we expect the ML model size to grow more than double. So for example, if we take BERT, which is a very popular natural language processing model, it has millions of parameters, and the latest one, the GPT-3, has billions of parameters. But BERT specifically takes 9 hours to train on the best single available server with GPUs. So, and this is not ideal, right? No training scientists want to wait for 9 hours to get the results.
No.
So yes, exactly. So this is where the scale comes in. The way ML models solve this problem is to scale in terms of teraflops, which basically means using more GPUs for computation. But when you do that, then there are more components come into play for which affects performance. And one of such components is networking. I think the biggest challenge with networking, biggest challenge with scale is that there would be lots of communication across nodes, and there is computation going on all of the GPUs. So we have to maintain a balance between the communication not affecting the computation. And this is where the need for a fast interconnect, such as elastic fabric adapter, is required.
I know from HPC applications, the thing that the EFA does I think it's the thing that's quite remarkable about it that moves the needle. It's that swarm-like message delivery, because you're not, this has always been my objection to using things like MPI ping pong as a measure of HPC performance, or at least as a predictor of HPC performance, because very few real codes actually are bothering to send a single message back and forth, and having a single message back and forth being the gatekeeper for performance, right? They send thousands of packets or millions of packets.
True.
It's a massive.
Yeah,
load.
That's so true. It's basically obsessing over single packets. Ping pong latency is basically trying to solve a traffic issue by saying, okay, this single car was responsible for the delay of the entire traffic.
Right. No, so. In fact, I often say that it's sort of like somebody who lives in New York City figuring out that, or coming to the conclusion that they're going to get to work much faster if they drive a Ferrari. But it's bumper to bumper in that city, and there's no way that they're going to move any faster than a bicycle.
True. Now we have to zoom out into what customers need. And most of the ML training application uses GPUs for training these applications.
Mm.
And NVIDIA's have come up with a library called as NVIDIA's Collective Communication Library, which basically enables all these machine learning training applications to do communication in a performant way. So Nickel basically implements all collective primitives such as like all reduce, broadcast, all gather, and they have been performing. They work well in with GPUs, and they enable multi GPU and multi node communication.
Then we go further up the stack, right? Because it's Nickel, of course, is its middleware. What's the next thing up? I think the next thing up, and actually, you've got some graphics on this, I think. So,
Yeah. Sure.
This, of course, is way up the stack, right?
Yes. So it talks about the entire machine learning training stack and how it looks like on AWS cloud. So you can see like at the start of it, there are machine learning training models. Now, these could be anything, natural language processing models, object detection models, or anything that the crazy ML world is up to right now. And all of these training models uses different kind of frameworks, which basically helps them to implement the models. The popular ones are PyTorch, TensorFlow. Below that, all of these frameworks support different kind of backends to do communication, to do collective communication. Now, the work that AWS wanted to do was to allow all of these customers who are doing ML training application to seamlessly move to cloud and with no change in their application, and like optimize all the software stack so that they get the performance they need at scale. So below that is our whole networking stack. We have first the AWS OFI Nickel plugin, which basically enables Nickel's networking pattern to use Elastic Fabric Adapter. So plugin is an open source library. So you guys can like go out, check out what it does. But basically it is trying to map the Nickel's communication pattern to libfabric EFA provider, which and libfabric, like just as a background, libfabric is a hardware agnostic library which lets applications do network transfers without caring about the underlying hardware.
Right. So and in fact, we use libfabric to interface into Intel MPI and OpenMPI and MVAPIC and a whole bunch of other things. So
exactly. And here in libfabric, we have a EFA provider component to it, which enables to interact with the EFA hardware, which is like the bottom second layer, which is the actual hardware NIC device. And then we have the underlying EC2 infrastructure. So from the customer's perspective, they can bring in their ML training model and the framework, and that would just seamlessly use EFA without any changes in their code.
And it's important, like, I think it's important to highlight something you just said there, which is that, from EFA all the way up, in fact, from the EC2 hardware layer all the way up, all of these different layers are all interfacing with open standards. So there's a whole pile of open source code there from Open Fabric and the OFI Nickel plugin and Nickel itself and all the way up. But, all of this is open standards and open source. So that, like you said, nobody needs to change a single line of code in their own application, and their applications that run here are going to run perfectly fine elsewhere. So that makes applications really portable.
That's true. And I think we are working, like all of the AWS teams as part of EFA networking are working on each of these layers and like optimizing it, not just for Nickel communication pattern, but as you mentioned, Intel MPI, Open MPI, and everything like HPC workloads as well. So we spend our efforts on, so I think the core thing to highlight over here, which applies to general Annapurna too, is basically when you own the entire software stack, including the hardware, you have so much more things to tune for the customers. And this is the benefit of like Elastic Fabric Adapter in general. And we also contribute that back to open source because most of the software libraries are open source. In the Trainium world, though, we do a lot because there we are working on enabling a new accelerator on off these. So basically introducing a new backend to these frameworks so that the ML training model seamlessly when they run on AWS hardware, which has our accelerators, can use it without much change in the code. So we do a lot of work in these ML training frameworks for introducing the new accelerator. Yeah, this one is focused on understanding what EFA, which is like the RDMA-based networking, brings to the table as compared to what AWS used to support, which is TCP multi-stream. So it's a simple test where we are mapping the Nichols bus bandwidth. So basically take any kind of nickel collectors like all reduce and like what kind of network bandwidth it sees depending on different sizes. And as you can see for like sizes of the order of gigabytes, EFA is like 3x better than what TCP offers. So this is like the huge gain.
Cool. Now let's go and talk about the actual performance. Like once
exactly. So this was more, yeah, this was more like micro benchmark comparison just to see how Nickel would do with EFA. And now what's more important to the customers is to see how their ML training models are going to do. So going back to the example that we started off with, which is like BERT on a single node. So basically on the x-axis here, we have the number of GPUs, and each single server that AWS has 8 GPUs. So basically the first column basically means single server. And on the y-axis, we are talking about the training time. Like BERT large, using the TensorFlow ML training framework, it takes 9 days, 8 hours to train on a single server.
And actually, it's a single server with 8 GPUs, which is kind of, I mean, by the way, that's sort of unrealistic anyway. In most people's experience,
exactly.
They're not going to have 8 GPUs in their servers. But you know, that's
yeah. I mean, these are very powerful CPU, powerful GPU like servers. It's expensive too because it has 8 GPUs.
Right. All that GPU silicon is not cheap. Hey, hello NVIDIA. Anyway. But that goes, so 9 days down to an hour.
Yes, and that at a scale of 2048 GPUs in a cluster, which is like I think 256 AWS servers.
Yeah, that's exactly I just did the math then. That's right. That's not exactly a numerically large cluster, and we've thumped it down to an hour.
Yeah, basically just go for lunch, come back, and you have your training done. Voila.
That's kind of neat. I like that. Well, you know, we always we always say that it takes an awful long time to grow a new scientist, whereas you can scale GPUs and CPUs anytime you want. So the most expensive part of the cluster is the person waiting for the result. You've got a workshop, or at least a how-to guide, getting started guide, up on the interwebs, and I'm going to put the address into our notes as I talked about a minute ago. I noticed that it gives you multiple options depending on whether you want to start with your own base army or start with the AWS Deep Learning Army. The Deep Learning Army is kind of a one-stop shop for like all of these frameworks, all of the stack. It's fully integrated. You just know it works, and it's kept up to date all the time by the DL Army team. So
that's right.
Kind of handy. All right. Well, hey, thank you for coming along and talking about that this week. Really appreciate it. We'll definitely, we're going to have you back to talk about some interesting customer workloads, I think.
Yes.
At some point in the future.
We would love to cover that too. Yes. Thank you.
There is. All right. Well, hey, for anybody else who are watching at home, if there's any other topics you want to see us cover in future Tech Shorts, anything else you want us to dive deep on, or if there's something that you heard today that you want us to go further on and uncover some more details, find us on Twitter. Our DMs are open. But until the next time, thanks for listening today. We'll see you soon.
Thank you.